Can you guys hear me now? Can you hear me now? Yes? Okay, thanks.
Yes.
Okay, great. All right, so I'm gonna do, all right. So on the reminder items again, homework 5, I extended for one more day because last night there was power outage on campus. So if you didn't get a chance, you can still finish your homework number 5, okay? Homework number 6 is due on Sunday, this Sunday. Exam 2 is due on Friday, okay? So again, I apologize. I was late because one of the previous physics professor, she was looking for something in the lab. We couldn't find something, but it took us a while. But thanks for waiting. All right. So today we'll be looking at chapter 7. This is a new chapter that will not be on exam 2, but we'll just keep lecturing. Okay. So this is work and kinetic energy. Okay, we'll take a look. So I think in our daily life, we talk a lot about work, like homework, housework, or you are doing a lot of work recently. But in physics, we kind of define work differently. Okay, so in physics, the work is defined as when you have force acting on an object, then the object, if the object moves under the influence of the force, okay, so then there's some work done by the force. So for the simplest scenario, we can assume if you are pushing a box over here across the floor, and say if you move distance d, so then work done by this force is equal to the force times d, okay? It has a SI unit of Newton times meter, or we call it joules, J for the symbol, okay? So that's the simplest case. All right. In general, you can apply a force, but then the object is not necessarily moving in the same direction as the force. Okay, so for example, if you are pulling your suitcase in an airport with this force has an angle of theta with the horizontal direction here, but your suitcase is moving in the horizontal direction, so they are not necessarily in the same direction. Okay, so then in this case, you can resolve the force into the horizontal component and vertical component. Okay, so then the work is work done by the force would be the just the horizontal component times the distance or displacement of this suitcase. Okay, in the vertical direction, they are perpendicular to each other. Okay, so let me stop sharing and then reshare. Sorry, looks like it didn't work out well. Thanks for the feedback. Okay, you can see the PowerPoint now. All right, so maybe let me go back one more slice. Or maybe I'll have you guys start from the first slide. Okay, so this is the reminder item. Homework now 5 is due tonight. Homework 6 due on Sunday. Exam 2 is on next Friday. For the work, so this simplest scenario is when you have force, when you push a box and then the box is moving in the same direction as the force. So then the work is done is equal to force times the displacement. Okay, and SI unit for work is joules, which is equivalent to Newton times meter. So in general, you might have force in one direction, but your displacement in a different direction, okay? Or having an angle with your force. So then you'll resolve the force into the direction along the displacement and then perpendicular to the displacement, okay? So then the work is done is equal to F cosine theta in this scenario, which is the X component or the horizontal component of the force times the displacement. Okay. And because multiplication are commutative, so you can move the cosine theta to the end of the equation here. So FD cosine theta. Okay. So if the force and displacement has angle, then it's that guy. Now, when the force is perpendicular to the displacement, then um, it will do zero work, because if when you do FD cosine, okay, cosine of 90 will be equal to zero. Okay. All right. And then you can think about it as another way here. So because work is equal to F times D times cosine theta, so then this is actually equivalent to if you are doing dot product of the force vector and then displacement vector. Okay, so remember when we talk about product multiplication, if you have two vectors, dot product multiplication of the vectors. Okay, if you do F dot D, then it's FD cosine. All right, so you can express in the vector form as well. All right. Or let me just show you on the figure here. So in this case, on the figure here, so if the force and displacement has angle theta, then it's equal to FD cosine theta. And in this case, if you are carrying a suitcase, you are walking in one direction. Now the force on the suitcase you exert is in the vertical direction. So then the cosine of 90 is zero. So in this case, you are doing zero work to your suitcase. Okay. All right. Now let's take a look um quick exercise here. So it says you have a 57 kilogram packing crate. It's pulled with constant speed across a rough floor with a rope that is at an angle of 37 degrees above the horizontal. If the tension in the rope is 142 newtons, how much work is done on the crate to move it 6.10 meters? Okay, so I'll have you guys try this one, and then we can take a look on the solution together. Okay. All right. So I see many of you guys have your responses in already, and they agree with each other. Okay. So that's good. So simply because this time the work, the force and displacement. This is the direction of the displacement. Okay, and then this is the force. So they have an angle of theta. So then you'll be doing F times D times cosine of the theta. Okay. Now for the weight, mg and normal force, these two will cancel out. Okay. And then so then it will be just this guy, this pulling force, the tension in the rope, and then this. Okay, we'll do the work. So it's 142 newtons times 6.0 meters times cosine of 37 degrees. Okay, so then that should be 100 or 692 roughly. Okay, you can round it up. Joules. Okay, that's the unit. All right, or meters times newtons. Okay, so I think I saw one response is having newtons over meters, so that's not the exactly correct unit. It should be meters times newtons or newtons times meters. Okay, all right, let's see if I okay, any questions you guys might have? All right. If not, then we'll move on here. So this is kind of summarized on the work done by a single force, a constant force, F. Okay. So if the angle between the force and displacement is in the range of minus 90 degree to 90 degree, then it will give you positive work. Okay. So then work done by this force is positive. If the force is perpendicular to the displacement, then cosine of 90, either positive or negative of 90, that equals to 0. So then work done by this force will be 0. And then another scenario here, if the angle is greater than 90 degrees, but less than 270 degrees, then you'll have negative work. Okay, so you might have a force that is pulling on the object, but actually the object is going in that direction. Okay, so then work is negative in that scenario. Okay, so work can be positive, can be 0, can be negative. Okay, depends on the angle between the force and the displacement. All right. Now, if there's more than one force acting on the object, okay, so then you can actually find work done by each individual force, or then you can add the total, add all the work up to be the total work, or you can actually figuring out the net force, the total force first, all right, and then use that total force times the displacement times cosine of the angle the total force makes with the displacement. Okay, so either way, you can calculate for the net force first, then calculate the work, or you can calculate work done by each individual force, then add them up to be the total work. Okay. So next we'll be going to looking at if work is done by a varying force. Okay, so that means the force is not always constant, so it either changes direction or changes magnitude with time. So in that scenario, then you cannot use F times D times cosine because F might be changing, all right, and then the theta might be changing as well. So then you have to do this in with the integral. So you are going to write out the differential form of the work. That means you are taking a very small displacement delta r or dr on the path, okay, and then do the force times dr, and then you are going to do integration through that path. If you are going from point A to point B, then you are integrating through that path, okay, for the total work that is done on the object from point A to point B. Okay, so this is what you are going to do if you have varying force, right? Either the change in the direction or change in magnitude. Okay, so you can see you can write this also in the vector form. F dot product of dr, which is in vector form. So this dr is the smallest, the infinite small displacement. Okay, you are taking. So this is F dot that guy. So you can break this into 3 dimensions. You can use the components. So you can do the x component. So basically it will be fx dx, and then the y component fy dy, and then the z component fz dz. Okay, and then you can add them up to be the differential form of the work done by this variant force. Then you can integrate through, okay, the path from point A to point B. All right. Um, So that's the case when you have varying force. Now, if you have the next, we are going to look at work done by a few forces that we checked earlier in the previous chapter. So the first one we are going to check is work done by a normal force. Okay, so because the nature of normal force, so normal force is always in the direction that is perpendicular to the surface of the contact. So then a lot of times when you have the object that's moving on a surface, then normal force is going to be perpendicular to its displacement or at all the time, okay, or dr at all the time. So then if you are looking at the force done or the work done by the normal force in dot dr, because they are perpendicular to each other, cosine of 90 degree will be 0. So then work done by normal force is going to be 0. Okay, so work done by a normal force is always 0. All right. Um, Another force would be the frictional force. Okay, so because of the nature of the frictional force is always opposite to the motion or attempted motion between the object in contact. Okay, so if you have object moving on along the surface, now in this case, then friction force is opposite to the displacement. So this guy and this guy would be in opposite to each other. Okay, so that means cosine of the angle theta between these two will be in the because they are opposite to each other. So then the angle between these two vectors is 190 degrees. Okay, so cosine of 100 or 180 degrees, cosine 180 degrees will be -1. Okay, so then that gives you this minus sign. Okay, so then it will be negative. All right, so work done by a frictional force that should be negative. Okay, and it depends on the distance the object did travel, because friction force, if n is fixed, then it's fixed force. Okay, so then it's just depending on the path. All right. Another special force that we mentioned earlier is the gravitational force. Okay, so for gravitational force, it's equal to mg, and then the direction of it is always downward, okay, in the negative y direction. All right. So then in that sense, when you do the dot product of the force mg minus mgj times the change in the displacement, okay. So remember, if you have for the force here, okay, so let me show you on the paper here. So the weight is equal to minus mgj, right? So its I component is 0. So it's pretty much like 0I minus mgj, all right? So if you remember, if we have two vectors dot product, if this is two-dimensional, then it's equal to ax bx plus ay by, all right? So if one component is 0, then this guy will be 0, okay? So then it will be just ay times by. In this case, it will be just the mgj, okay, or minus mgj times the y of the displacement, okay? So then yb minus ya in that case, okay? So it will be just this guy. When you are doing just the component, it will be ay times by, okay? So in that sense, for the work done by gravitational force, it's going to be equal to the weight mg times the change in the y coordinates, the vertical positions of the two. Okay, so if we go from point B to point A, so it doesn't matter if you are going from, say, from here, this is your A, this is your B, okay, or you are going along a path like this, going from A to B. All right, so these two paths, like directly straightforward from point A to B, or you are kind of zigzag or curved around like that. So work done by gravity will be the same, okay, because the initial A position in vertical and Y position in vertical, they are the same. Or you can have like from here and then to here, another point C, if the object goes from there, A to C, and then from A to B, these two paths work done by the gravitational force should be the same. Okay, it's only the initial Y position and final Y position that matter. Okay. All right. So it's only determined by its initial and final positions in Y direction. Okay. It's not relevant to the X position. All right. Now, another force that we mentioned in the previous chapter is the spring force. It's force exerted by a spring, okay? So that force is equal to K times X. And then that force is also in the opposite direction of the displacement. For example, if you are pulling this spring to this side, to the right, then the force by the spring will be to the left. If you push the spring to the left, then the force will be to the right. Okay, so you can see the F and delta X, or the change in position, they are in opposite direction. All right. So, and then this force F, it's a varying force, depends on the delta X. Okay, so it's not a constant force. So then you want to do the integration. So for the force that is, or for the work that is done by a spring force, you are going to do integration from point A to B, and then F times dx. Okay. Then in that sense, you are doing, so we can just write x instead of s, delta x. Okay, so then work done is equal to kx dx, right? If you are going from point A to point B, A to B, all right? So then, and then with a negative sign because they are opposite to each other. Okay, so there's a negative sign there. So then equals to minus, if you are doing integration of kx, that gives you minus 1/2 kx squared, all right? So then from point A to B, okay? So then it's equal to minus 1/2 k of xb squared minus xa squared. All right, so that's work done by a spring force. In general, so for a spring force, because it's linear, so it's 1/2 kx squared of b minus x squared of a. But in general, if you have varying force like this, okay, it's a non-linear function, then you can actually calculate the area underneath this guy. That's actually when you are doing integral, right? Integral of f(x) dx gives you the area under that curve. Okay, so then in general you can use that. You can calculate the area under a curve. Then you can calculate what's the work done by a force. Okay, a varying force. All right. Um, we will take a look on the second example here. So in this case, it says a bungee cord exerts a nonlinear elastic force of magnitude Fx equal to K1x plus K2x to the Q, where x is the distance the cord is stretched. K1 is equal to 204 newtons per meter. K2 is equal to minus 0.233 meters per newtons per meter cube. It says how much work must be done on the cord to stretch it by 16.7 meters, right? So in this case, then you'll be doing the integration, right? Because this force now is a varying force. So then work done should be equal to the force F as a function of x, all right, dx, okay? So I'll have you guys try this, and then you are integrating from 0 to 16.7 meters, right? That's how much the cord is being stretched. All right, give it a try, and then we can take a look on the solution together in a few minutes. All right. So I think most of you guys have your responses submitted, so we can take a look here. So you're integrating from 0 to 16.7 meters, and then the fx is equal to, in this case, the kx, k1x plus k2 x to the q, all right, 16.7, and then dx. So the first term will become 1/2 k1x squared, all right? The second term will become 1/4 kx to the 4, all right? And then the limits is from 0 to 16.7 meters, okay? When you are doing definite integrals, then you don't have the constant term. You just plug in the upper and lower limits there, all right? So then we know K1 and K2, they are given. We can plug in the numbers. So then work done is equal to 1/2 of K1, which is 204 newtons over meter, times 16.7 meters squared plus 1/4. K2 is minus 0.233 newtons per meter cube, 16.7 meters to the fourth. Okay. So this is what you have when you plug in the upper limits into the x. Now, when you do the lower limits into the x, it will be 0. Okay, so minus 0 plus 0 for the both terms. Okay, for this one, it becomes 0. This one will become 0. Okay, so you can ignore the when you plug in the lower limits into the equation there. So this will give you about 23.9 times 10 to the 3 joules, or 23.9 kilojoules. Okay, I think that's more accurate to say. Okay, so most of you guys have this one correct. Okay, except there's a number that is a little bit less than 23.9 kilojoules, and that might have to do with the when you plug in these numbers over here, or when you plug in the numbers. Yeah, yeah, compare to see where you got that wrong, but most of you guys got this right. Okay, any questions you guys might have? Okay, so if not, then we can continue here. So that was the first section. The first section talks about work done by a constant force, a varying force, and then some special forces. Okay. The next two sections talks about kinetic energy and work energy theorem. So I figure it will be easier to understand if we talk about these two at the same time. Okay. So we will start from the one-dimensional. Okay, the force, you just start from one dimensional, and then we can expand the theorem to two dimensions. Okay, so that's just assuming for the one dimensional kinematic equation. So we are going to pick the last one in the one dimensional, the 5 equations. If you guys remember, the last one is about final velocity square equal to initial velocity square plus 2 times acceleration times x minus x naught. And then in this case, we are assuming the acceleration is constant, okay? Also, we learned Newton's second law, which says force equal to mass times acceleration, all right? And then we just learned this new concept of work done. So if this is a constant acceleration, that means net force is constant. So then it will be F times D, because this is one-dimensional motion right now. So F and D are in the same direction. Okay. So we'll just use this the simplest case that for the motion here. So F times D, under the influence of F, that object moves in the direction, the same direction. Okay. So then the distance traveled should be minus final x minus initial x. Okay, so with this, so now let's take a look on the algebra that how I get to the equation down here. Okay, so basically work is equal to force times x minus x naught, right? And then if you are looking for the first equation list on the slides right now, so then x minus x naught is equal to, in that case, because you have v squared equal to v0 squared plus 2a x minus x naught. All right. So then you can express x minus x naught, okay, in terms of the other variables. So that will be v minus v naught squared equals 2a x minus x naught. You move this guy to the other side equation. Now both sides you divide them by 2a, get rid of 2a. So then this is x minus x naught. Okay. So then also for the force, it's equal to m times a. So then you are going to replace this expression for the x minus x naught, replace the force by m times a there. Okay. So then work equals to m times a times v squared minus v0 squared over 2 times a, right? So then acceleration and acceleration will cancel out. All right. So then you'll have 1/2 or m times v squared. You have m times v squared divided by 2. So that means 1/2. And then for the second term will be similarly 1/2 mv0 squared. Okay. So then work is equal to 1/2 mv squared minus 1/2 mv initial squared, right? So basically, this is the equation in red on the slide here. So this tells you work done by a force is equal to this quantity initial or this quantity final minus this initial, okay, related to the V naught, okay. So you can see this term and this term has similar expression. It's just related to their mass and the velocity. So we kind of give this term 1/2 mv squared to a new name to it called kinetic energy of the object. Okay. So then work done is equal to kinetic energy, the final kinetic energy of the object minus the initial kinetic energy of the object. Okay. So that's basically the work energy theorem. So define a new quantity called 1/2 mv squared, which is the kinetic energy. All right. Then we can have the work energy theorem, which says work equals to the work done by on the objects equal to the change in the object's kinetic energy. So change in kinetic energy means final kinetic energy minus initial kinetic energy. Or in the last equation here, work equals to kf minus k initial. Okay. Now take a look on the kinetic energy here. So sometimes you see people write kinetic energy in this term, especially if you were going to study quantum physics later on. And most of the time it's expressed as momentum squared divided by 2m, okay? Which momentum is defined as m times v, which we'll mention later on in the class, but this is the definition of it. Just in case you encounter this expression, that means kinetic energy is equal to p squared over 2m, where p is the momentum. Okay, it's the same thing here. So if you plug p as mv here, you can see this is m squared v squared, then it's 1/2 mv squared. Okay, so it's the same thing. All right, but basically, this is the work energy theorem. Okay, and then this is the kinetic energy definition of it. Okay. Now, because you can see from the work energy theorem over here, work is equal to change in kinetic energy. So if work has a SI unit of joule, then kinetic energy should have the same SI unit of joule. Okay. So then for kinetic energy, it should have SI unit of joule. It's not listed in the PowerPoint, but that's the SI unit. Okay. All right. So then we have connected work energy theorem derived in one dimensional. We can also expand this into 3-dimensional, okay? And then in calculus form. So in calculus form, then because in calculus form, the network is equal to the net force times the displacement, okay? D of displacement. And net force is equal to mass times derivative time derivative of velocity, which means acceleration. Okay, so this is F equal to m times a acceleration written in time derivative of velocity form. Now, if you combine these two together, so replace this guy, the net force, with this expression over here, then you come to this expression here. So differential form of the work equals to mass times dv over dt times dr. Okay. Now you can do dr over dt instead of dv over dt, right? So then dr over dt will be dv, right? Because it will be v, all right? And then dv remains over here. So it's becoming m times dv times v, or m times v times dv. You can move the v in front of the dv. Okay, so then this is this guy. So then the differential form of work is equal to mv times differential of the velocity. So you can set this guy equal to that guy, and then you can do integration. Integration of this side, the right hand side will give you the net work, okay, from point A to B, and then integration of this will give you the change in the kinetic energy, initial and final. So in this form over here, because if you are doing m dvx dvx, then this gives you 1/2 mvx square, okay? And then on this one, mvy dvy will give you 1/2 mvy square, right? Similarly for this guy, all right? And then you single out the common factor of 1/2 and m, and then this is the velocity component, xyz component, which means the its velocity magnitude square, okay? And then from point A to B, all right, which means you are doing 1/2 mvb square minus 1/2 mva square, which is kb minus ka. K stands for kinetic energy. Okay, so this is how you can derive from the calculus and in 3D. So basically, this will be the same results if we just check one dimensional by one dimensional. Okay, one dimension by one dimension. All right. So next, let's take a look on this example here. This one is about the work done, okay, by the bumper, the car's bumper. So the car's bumper is designed to withstand a collision, which is 4.0 kilometers per hour collision with an immovable part without damage to the body of the car. The bumper cushions the shock by absorbing the force over a distance. Calculate the magnitude of the average force on a bumper that collapses zero point 0.2 meters while bringing a 900 kilogram car to rest from an initial speed of 1.1. Okay. So on this one, you can imagine that for the collision happen, so then for a car, if hits another car, okay, so it's assuming the 900 kilogram cars hits another car that's stationary, all right, so then the mass of the car is 900 kilogram. The initial velocity, v0 or vi, that should be the 1.1 meters per second or 4.0 kilometers per hour. Okay, we are going to use this one. The final speed will be 0 because it's been brought to rest. Okay, so yeah, and then try to use the work energy theorem here. You can solve for the force, the average force, by calculating what will be the, and then the distance travel. Sorry, distance travel is the 0.2 meters. Okay, you can solve this by using the kinetics and then Newton's second law, but try to see if you can use the work energy theorem here. Okay. Try to see if you can use this equation up here, and then with the work also equal to the average force that you are looking for, times the distance that the car travel. Okay, so try to see if you can use this too. All right. I see many of you guys have submitted your responses, and they look like most of you have agreement with the magnitude at least. Okay. So we can take a look here. So for the work done on the car, we can calculate using this equation, right? So work done equals to the final kinetic energy minus initial kinetic energy. All right. You can plug in the numbers here. Let me see. I don't quite use that, but I use this one and then also this guy here. So work done is also equal to force times average force times the distance travel. Okay. So then I set these two equal to each other. So I set A average times D equals to 1/2 mv square final square minus 1/2 mv0 square. So then my F average is equal to this 1/2 m. I can single out m, okay, so v squared minus v0 squared divided by d. All right, so I don't have to plug in 1/2 and m twice into the calculator. All right, so this is 1/2 times the mass of 900 kilograms times final velocity 0 minus initial velocity 1.1 meters per second square here. Okay, divided by the distance traveled 0.200 meters. All right, so then I end up with the average force being minus, so roughly minus 2.7 times 10 to the third newtons. Okay, so it's minus, it tells you that the average force the car experienced is in the opposite direction of the initial velocity. Okay, so we are assuming initial velocity to be positive, so then that's in the opposite direction. Okay, I do see some of you guys have that minus indicated. Okay, so that's absolutely right about it. Okay, let me see. Any questions you guys might have on this one? All right. So if not, I think we are going to stop here for today. In the PowerPoint slide, there's another example right after this. Okay, so if you guys find the chance after class, you can check on that one, maybe getting started to work on this one, but we can take a look on this one together next time. Okay, so I will see you guys tomorrow in class then. Bye.
Thank you. Have a great day.
Thank you too.